In this video, I will give a short overview about our paper, SO3, or Special Orthogonal Group Invariance of Informed Graph-Based Deep Neural Network for Anisotropic Elastoplastic Materials. The work on this paper was carried out at Columbia University in the group of Professor Wang Sun. And the highlights of this paper: first, we wanted to design a machine learning based constitutive model for crystal plasticity. In this, we try to enforce the objectivity or the frame invariance through changing the representation of the tensors to be in spectral form. And then this new form allowed us to design new laws or objective functions for the training of the machine learning model. And we made use of the hierarchical relations among the physical quantities and state variables to generate informed directed graph. So in the second section in the paper, we introduced different informed directed graphs. These three variations here. We have directed graph, which is non-informed. So we have the strain and strain history to generate the stress in the current step. Or we have informed directed graph, where we made use of the stress from the previous time step to improve the stress prediction in the current time step. And then the last variation was the return mapping informed graph, where we made use of the most of the data which were generated during the generation of the database. So we applied the return mapping for the database. So we made the same steps in the generation of the machine learning material model, and we discussed the accuracy of the prediction. In the third section, we talked about the objective function of our machine learning material model. And we discussed, of course, the spectral form representation of the matrices. And this is a very important issue, because maybe for the same database, we can generate a good or a bad material model, depending on the way you treat the data. So in this connection, the spectral representation allowed us to generate or design neural loss functions. For instance, the eigenvectors could construct rotation matrices, and from this, one of our loss function was the distance between two rotations. For instance, the Euclidean distance between the Euler angles of these rotations. Or alternatively, we made a mapping between Lie group to Lie algebra, so to the tangential space, and then this new way of representing the rotation matrices allows us to design a new loss function in the Lie algebra, and this was something new. And then in the fourth section, we discussed the supervised machine learning. Of course, we used recurrent neural network because plasticity is a path-dependent process, so feed-forward neural networks will not be applied, or cannot be applied here, or will not be accurate. And then in the fifth and sixth sections, we talked about the generation of the database. It's for crystal plasticity, so we considered face-centered cubic crystals. We discussed the different loading scenarios. So at the end, we had a database of 1,176 different experiments. And we also trained the model, and we showed that our trained model, when it's tested on unseen data, it can really yield very good predictions. And the methods which we figured out that to be the best in this case was the informed graph, the method DG1, so the simply informed graph with Lie algebra for the representation of the rotation. So if you are interested in this paper, please check the description of the video where I'm putting some links. And if you have any question, please don't hesitate to contact me. And thank you so much for your attention.